Hello friends, in this video I am going to solve problems on first law of thermodynamics applied to closed system. In this problem, 1.5 kg of liquid having a constant specific heat of 2.5 kilojoules per kg Kelvin is stirred in a well-insulated chamber, causing the temperature to rise by 15 degrees Celsius. Find delta E and W for the process. If same liquid is stirred in a conducting chamber during the process, 1.7 kilojoules of heat are transferred from the liquid to the surroundings, while the temperature of the liquid is rising by 15 degrees Celsius. Find delta E and W for the process. So there are two cases. The first one is it is insulated chamber. It is well insulated chamber, and the other one is conducting chamber. One is insulated and the other one is conducting chamber. First let us calculate delta E and W for insulated chamber. For that, as usual, we have Q equal to delta E plus W. So here whatever the work that is transferred to the system will be converted into heat, and that heat will not be transferred from the system to the surroundings, as the system is completely insulated, and that addition of heat in the form of work transfer to the system will increase its internal energy. So now let us calculate the amount of heat equivalent of work that is transferred to the system, and the supply of work will raise the temperature of the fluid by 15 degrees Celsius. So here we can take delta T is 15 degrees Celsius, and we have its specific heat at constant pressure as 2.5 kilojoules per kg Kelvin, and then we have mass equal to 1.5 kg. So we have formula to find out heat equivalent of work, that is Q equal to M into Cp into delta T. Here T2 minus T1 is directly given, that is 15 degrees Celsius. So here the value of M is 1.5 kg, and its Cp is 2.5 kilojoules per kg Kelvin, and delta T is 15 degrees Celsius. So the value of Q is 56.25 kilojoules. It is 56.25 kilojoules of work is supplied, is converted into heat when it is stirred in a well insulated chamber. So since there is no heat interaction, and this Q is added, that is equivalent to W. Here work is done on the system. So let us substitute the values to this equation. We will have Q equal to delta E plus W. So since it is well insulated, it is 0 equal to delta E. Here W work is done on the system, so it is minus 56.25. So here the change in internal energy is delta E equal to 56.25 kilojoules. So in that process, work that is supplied is minus 56.25 kilojoules when there is 56.25 kilojoules of heat is transferred, work is transferred to the system. It is converted into heat and which is stored in the system as internal energy, as it is completely insulated. So there is no heat transfer. Heat transfer Q is 0. Now the another case is a conducting chamber during which heat transfer Q is 1.7 kilojoules, and here the same mass of liquid as a temperature rise of 15 degrees Celsius. So the change in internal energy delta E is the same as the previous one, so it is 56.25 kilojoules. Then its W, what will be its W? So for that we have the formula Q equal to delta E plus W. Here Q is it is minus 1.7 kilojoules. We have taken the negative symbol because heat is rejected from the fluid, that is system. That is equal to delta E. Delta E, the value of delta E is known, that is 56.25, so it is minus 1.7 equal to delta E is 56.25 plus W. The value of W is equal to minus 57.95 kilojoules. So there is a 1.7 kilojoules of heat leak into the surroundings, so that compensatory more work has to be supplied. So that's why the work that is supplied to the system by stirrer is minus 57.7595 kilojoules, which is 1.7 kilojoules more compared to the work that is supplied to the insulated chamber. And in the next problem, that is also once again first law applied to closed system. For that let us consider an electric generator coupled to a windmill produces an average electrical power output of 5 kilowatt. The power is used to charge the storage battery. Heat transfer from the battery to the surroundings occurs at constant rate of 0.6 kilowatt. Determine the total amount of energy stored in the battery in 8 hours of operation. So here electrical generator that is coupled to the windmill has electrical output of 5 kilowatt. This power is used to charge a storage battery. So here work is done on the storage battery. So there will be W that is equal to minus 5 kilowatt of work is kilowatts of power is supplied to the battery, and for 8 hour operation we will have like this. It is minus 5 into 3600 minus 5 into 3600 into 8 hours. So here 5 kilojoules per second is converted to kilojoules per hour, and there will be 8 hours of operation. So the total work that is supplied will be minus 1,44,000 kilojoules of work is supplied in 8 hours of operation to the battery. So that is W. Then there will be heat leakage to the surroundings at a constant rate of 0.6 kilowatt. So here heat is rejected from the battery to the surroundings. So here battery system. So it is once again minus 0.6 kilowatt. So to convert the amount of heat that is rejected to the surroundings in 8 hours, so it is once again minus 0.6 into 3600, multiplication of 3600 will convert the total amount of heat transferred to the surroundings in 1 hour, and there is an 8 hour of operation. So there will be total of 17,280 kilojoules of heat is rejected to the surroundings. So here we should find out the total amount of energy stored in the battery, that is delta E has to be calculated. Delta E has to be calculated. So first law, closed system undergoing process, we have Q equal to delta E plus W. Here heat is rejected to the surroundings, so it is minus 17,280 kilojoules equal to delta E minus 1,44,000 kilojoules. So finally delta E is 1.26 into 10 power 5 kilojoules. So 1.26 in 10 power 5 kilojoules of heat, that is energy, is stored in the battery. It is actually internal energy. The storage is called internal energy. So 1.26 in 10 power 5 kilojoules of energy is stored in the battery in the 8 hour operation, where 0.6 kilowatts of heat is rejected from the battery, and that receives 5 kilowatt of power.